we will talk about the damping and the role of damping in structural design of buildings. So let's start. You should always keep the main governing equation of motion for any dynamic system in mind while interpreting all the calculations and the concepts. So you start with the main equation mu dot dot plus cu dot plus ku equal to any dynamic force, applied dynamic force. For multiple degree of freedom systems, you know that this is mass matrix, then the acceleration vector, then C matrix, and then the velocity vector, then K matrix and the displacement vector equal to the applied force vector, which consists of dynamic forces. So we will discuss the focus will be on this C matrix in this lecture, which represents the damping mechanism in the dynamic system. You know, the construction of K matrix is straightforward. The K matrix is a function of cross-sectional dimensions, member sizes, and the material properties. But this is not the case with the damping matrix. It is impractical to determine the coefficients of damping matrix directly from the structural dimensions, structural member sizes, and the damping properties of structural materials used. The damping is generally specified in a structure by numerical values for the modal damping ratios. So you specify the numerical values of modal damping ratios, and these are sufficient for the analysis of linear systems with classical damping. At this stage, I hope you do understand what is meant by classical damping. I just quickly review the concept here. You know that due to modal orthogonality, this matrix phi, which is the capital Phi, consists of all the mode shape vectors. The transpose of this matrix multiply with the mass matrix, multiply with this matrix again, is a diagonal matrix. And basically this modal orthogonality property allows us to uncouple the governing equation of motion into modal equations. Similarly, the K matrix is also the phi transpose times K matrix into phi is also a diagonal matrix. In damping matrix, if we write phi transpose into C matrix into phi, if this is a diagonal matrix, then this is classical damping matrix, and if it is not diagonal, then it is non-classical damping. In that case, we will not be able to uncouple the equation of motion into n different modal equations. So the construction of C matrix is the primary focus of this lecture. So let's see how we can estimate the modal damping ratios. We just saw that the construction of C matrix requires modal damping ratios, unlike the K matrix, which depends directly on the structural properties, structural dimensions, material properties, etc. So for seismic safety assessment of existing buildings, ideally the experimentally measured properties should be used. That should also include damping. But for economy and time, sometimes it is not possible to actually experimentally measure the damping properties of the structure. For new buildings, the measurement is also not possible. So most of the times, the modal damping ratios for a structure should be estimated using measured data from similar structures. It may not be possible to measure it for each structure, so we must have a kind of a database for modal damping ratios, the typical modal damping ratios, which should serve as a guideline for selecting the modal damping ratios for a new structure or for the seismic safety assessment of an existing structure. So we need a comprehensive database, and we don't have such a database until now. So what we can do is that we can rely on different recommended values, and which are based on experience and based on the experimental trends of the measured values of modal damping ratios. Obviously, for ordinary structures, we will have slightly higher values of modal damping ratio xi, compared to the special structures, which should have lower values for conservative design estimates. Some guidelines, for example, for unreinforced masonry, a damping ratio of 3% is generally specified or recommended. For reinforced masonry, we have a value of 7%, and code specified value is for 5%. The spectra specified in building codes is mostly specified at a damping ratio of 5%. This table shows the recommended damping ratios for different structural configurations, as well as for two different levels of stress. The first level is the working stress level, no more than about half of the yield point. So we see that at this level, for different types of structures, for example welded steel, pre-stressed concrete, well reinforced concrete, you have a specified or recommended values to be used as modal damping ratios. At a stress level which is higher than the working stress level, which is just below yield or at yield, the values are higher. So it means that the modal damping ratios, as expected, should depend on the level of amplitude, the level of stress also. So we have higher values of modal damping ratios for same structures if the stress level assumed is higher. So you can use these recommended damping values as a guideline to select suitable values for your case. For linear elastic analysis with classical damping, what we do is that we start with the undamped case. We write the undamped case, the governing equation of motion. We solve it for free vibration response, we uncouple them, and we get n modal equations. Then what we do is that we use recommended values of damping ratios for all the significant modes of vibration. We use that damping value directly in the modal equations, and we solve them for different cases and we get the response. But this is okay for linear elastic analysis with classical damping. Let's see the construction of damping matrix, and let's have the analogy of the K matrix, which is the structure stiffness matrix, with C matrix, which is the damping matrix. The structure stiffness matrix, K matrix, depends on structural configuration and geometry and member sizes. It depends on cross-sectional dimensions. For example, the second moment of area I, which is also a function of cross-sectional dimensions. It also is a function of material properties like modulus of elasticity E, which directly enters in the computations. So the determination of K matrix is relatively a straightforward computation. But this is not true for the C matrix. It is impractical to determine the C matrix from structural details and material damping properties. Almost impractical, because most of the times the material damping properties are not well defined as compared to the material elastic properties like modulus of elasticity and other properties like Poisson's ratio, etc. So most of the times the damping properties are not well defined in case of damping. But even if they are well defined, even then the resulting C matrix will not account for several phenomena. For example, it will not account for a significant part of the energy dissipated in friction at steel connections, for example, opening and closing of micro cracks in concrete, or stressing of non-structural elements, for example, partition walls, mechanical equipment, fireproofing, etc., and the friction between structural elements and the non-structural elements, etc., and the list continues. So it means that the C matrix should not be merely a function of material damping properties. Otherwise, it will not account for several real phenomena. So there should be a more effective way of constructing this C matrix. So one way is, the most commonly used way is that you directly define the modal damping ratios, which account for all energy dissipating mechanisms. Some of the examples were shown in last slide. So you define these values considering in mind all those energy dissipating mechanisms and use those modal damping ratios to construct the C matrix. These modal damping ratios, again, I would say that they should come from recommended values, and those recommended values should be based on the available data on similar structures shaken strongly during the past earthquakes but not deformed into the inelastic range. Obviously, the damping values will not the damping values which will be determined from shakings which took structure beyond the elastic range will not be realistic in this case. Moreover, the classical modal analysis is strictly not applicable to nonlinear systems which have deformed, which already deformed into the inelastic range. Similarly, the classical modal analysis is also not consistent with the non-classically damped damping. So the available data should be based on the experimentation of structures which were shaken strongly during an earthquake, but not that strongly that they will bring those structure into inelastic range. So let's consider the most common case, the most commonly used case for the construction of classically damped matrix. And the assumption of classically damped matrix is a reasonable assumption if similar damping mechanisms are distributed throughout the structure. For example, a multi-story building with a similar structural system and structural materials used over its height. So in that case, the assumption of classical damping, that this matrix phi transpose C matrix into phi again, the big phi matrix containing all the mode shaped vectors, is a diagonal matrix. This assumption is reasonable in most of the cases when the similar damping mechanisms are distributed throughout the structure. So the most commonly used formulation for the construction of classical damping matrix is the Rayleigh damping. So we will discuss that in this lecture. Let's first consider the two simple cases, simpler than the Rayleigh damping, which is called mass proportional damping, this one, and the stiffness proportional damping, this one. Why it's called mass proportional for this case is that we assume that the damping matrix is a constant A naught, A sub O, multiplied by the mass matrix. In this case, we assume stiffness proportional damping, that the damping matrix is equal to some constant A sub 1 times the structure stiffness matrix. And since mass and K matrices are due to modal orthogonality, phi transpose multiplied by mass matrix multiplied by phi is a diagonal matrix, and same is true for K matrix also. Phi transpose K into phi is also a diagonal matrix. So these two are the examples of classical damping matrices: mass proportional damping and stiffness proportional damping. The units of this constant A sub O is 1 over second, and the unit of this A1 is second. So these two damping matrix formulations, mass proportional and stiffness proportional, are represented in model form here. So mass proportional damping would look like this, that if you have a multi-story building with 3 masses m1, m2, m3, the mass proportional damping will simply be represented by a dash pot at each story level with each mass with a constant A sub O multiplied by that mass of that story. Similarly, for stiffness proportional damping can be represented in this form, that the story stiffness of each of the stories is, let's say, K1, K2 and K3. Then the damping would be simply multiply, story damping will be represented by multiplication of this A1, the coefficient, multiplied by the stiffness of that story, K3, K2 and K1. So these are the two simplest models for formulation of damping matrix: mass proportional damping and stiffness proportional damping. So let's consider the construction of these matrices using the damping ratios for any particular modes, the modal damping ratios. We know that the modal damping ratio of any nth mode, xi n, will be the generalized modal damping coefficient Cn divided by 2 times the modal mass mn multiplied by the frequency of that nth mode. So where this mn is the diagonal element of this matrix, we know that this is a diagonal matrix with all entries equal to 0 with terms only in diagonals. The other end of diagonal terms are 0. So each of those diagonal terms will be the modal mass for any particular nth mode. So you can use that as mn here, and the omega n for that particular frequency, the frequency of that mode, and the generalized modal damping coefficient Cn. So if you can get these three things, you can calculate the damping ratio for any nth mode. So let's see what is the modal damping ratio for any nth mode for both of these formulations, mass proportional damping and stiffness proportional damping. Let's first consider the mass proportional damping, where the coefficient would become the generalized damping coefficient would in this case would become A naught times the modal mass mn of that nth mode, and we know that mn would be the diagonal term of the matrix, and that diagonal term would correspond to this term, which will be the phi n, which is the nth mode shape vector transpose multiplied by the mass matrix into the phi n again. So if you put these into the definition of nth mode damping ratio, this mn will be cancelled with this, and you will come up with this expression. So which shows that the nth mode damping ratio is inversely proportional to omega n, which is the nth mode natural frequency. What you can do is that coefficient A naught can be selected to obtain a specified value of the modal damping ratio in any particular nth mode. So you can set A naught such that you can get the required value of omega n for that particular mode. And you can construct the C matrix at the end using this expression. That C matrix will be just A naught, which will be known if you want to set a particular mode's damping ratio to a particular number, times the mass matrix of the structure. So this is the simplest formulation for the construction of modal damping, the structure's damping matrix. For stiffness proportional damping, you will also have the same equation, the modal damping ratio, and but in this case the diagonal terms, the Cn would be A1 times the diagonal entries of this matrix, phi, the capital Phi transpose K matrix into phi. So this will be a diagonal matrix in this case, and all the entries will be what? For example, for any nth entry will be basically omega n square into the modal mass mn. So this mn will be the diagonal entry, the corresponding diagonal entry of this matrix, phi transpose m into phi, capital Phi. So if you have the diagonal entry of this matrix, you multiply it with the nth mode omega n and square, then you will get the diagonal entry of this matrix. So you already familiar with these values. So you just put omega n square into mn into the definition of modal damping ratio, and you get for stiffness proportional damping that xi n is equal to a1 times omega n over 2. So in this case, unlike the mass proportional damping, the modal damping ratio is directly proportional to the nth mode. The nth mode modal damping ratio is directly proportional to that mode's natural frequency. So what you can do now is that the coefficient A1 can be selected to obtain a specified value of the damping ratio in any mode. For example, if you want to have a damping ratio of 5% for first mode, you will calculate the corresponding A1 such that the xi1 would become 5%, which is the modal damping ratio of the first mode. So with known value of A1, you can use this expression then to formulate the full C matrix. So in both of these formulations for determination of C matrix, you have observed one thing, and that is the variation of xi n as a function of omega n. In mass proportional damping, you saw that these are inversely related, and in stiffness proportional damping, you saw that they are directly related. But these two formulations, or this variation of modal damping ratio with omega n, is not consistent with the experimental data. The experimental data for different structures show that different modes of vibration exhibit roughly the same damping ratio for several modes. So as a step towards constructing a C matrix which is consistent with experimental data, we will see now the Rayleigh damping, which is basically the sum of mass proportional damping and the stiffness proportional damping. So in this formulation, the C matrix, the big C matrix, is constructed by multiplying A naught, a coefficient, a constant coefficient, with mass matrix plus another coefficient multiplied with the stiffness matrix. So the nth mode modal damping ratio in this case would become this, in similar to mass and proportional damping. Now the nth mode modal damping ratio would become this, and if you write this expression for any two specific modes, for example I and j, you can write these two equations in a matrix form also, like this. So now omega I and omega j are any two frequencies of ith and jth mode respectively, and xi I and xi j are their corresponding natural corresponding modal damping ratios. So the coefficients a naught and a1 can be selected to obtain the specified xi I and xi j for any ith and jth modes. You can solve this you can set a1 and a2 a naught and a1 such that you get the specified xi I and xi j for a particular ith and jth mode, which depends on your choice. So if the two modes are assumed to have same xi, which is very reasonable based on the experimental data, then in that case the two expressions will become this. So you can solve the two expressions simultaneously to get the values of a naught and a1. So in both of these cases, the damping ratio is constant for any ith and jth mode. So all you need to know is the natural frequencies of ith and jth mode, this one and this one, or basically this one and this one, to calculate these two coefficients. And once these two coefficients are known, you can construct the big C matrix using this expression. So this is the Rayleigh damping formulation. Let's see these three things in graphical form: this mass proportional damping, stiffness proportional damping, and Rayleigh damping. Let's see first the mass proportional damping, in which the damping matrix is equal to a naught times the mass matrix, and the modal damping ratio is shown by this expression. So if you plot the modal damping ratio with respect to omega here, which is the natural frequency, you will see this trend. Obviously they are inversely proportional, so the line will go like this. In this case they are directly proportional, the stiffness proportional damping, this one. So in this case, the modal damping ratio is directly proportional to omega n. So the line will be directly proportional like this. But if you add these two, which will give you the Rayleigh damping here, in that case the modal damping will be this. So if you plot this term on with xi n on y-axis and omega n on x-axis, you will get this solid line, this line, which is this one, this one, this one. The dotted lines are shown the two components. This one is the mass proportional damping and this one is the stiffness proportional damping, but this solid line is the Rayleigh damping. So for example, if you have the same xi for two different modes, one is the ith mode, will have a natural frequency shown by omega I, and the other one has another frequency, jth mode has a frequency omega j. If they have both the same damping ratio, so then it means that these 2 points can be our controlling points to control the shape of this solid line. So in other words, the modes I and j with specified damping ratios should be chosen to ensure reasonable values for the damping ratios in all the modes contributing significantly to the response. So all of those modes which have natural frequencies in between I and j will have almost same damping ratios, which is consistent with the experimental data. So these omega I and omega j should be chosen carefully so that all the important significant modes should be given or should be represented with a reasonable damping ratio, which should be close to or consistent with the experimental values. So now I will show you a model in Etabs and will show you how you can easily define these damping values while making a dynamic load case in Etabs. So I'll go directly to Etabs now. This is Etabs 2016 version, and this is a model of a 40-story building, and I will show you that how you can define the dynamic load case and the ground acceleration history. So you will go to define and then go to functions and then time history. Now in this model there are already some earthquake ground acceleration histories defined already, so I will just show you one, maybe this one, and I'll modify it to show you. So this is the ground acceleration history. The time versus ground acceleration graph is already defined in this model, and graphically it looks like this. So if you want to view the response spectrum of this ground acceleration history, you can go to this tab, this one, view response spectrum, and then see all the defined acceleration histories and their corresponding response spectra. So if you click on a time history defined, you will see the response spectra for different values of damping ratio starting from 0 up to 10%. So you can change these damping values, you can have different views of the response spectra, different views of the same graph. So now I will go to the load case, the dynamic load case, which is here. So, and I'll basically already a nonlinear direct integration history or dynamic step-by-step integration load case is defined already, so I'll modify it and will directly go to the point where you have to define the damping. So in this dynamic load case, you have to define damping here. In other parameters you can see a parameter named damping, and then you can modify it to see what are some of the options available for you to define damping. So now there are two options. One is viscous damping, viscous proportional damping, and the additional modal damping. Let's see first the viscous proportional damping. You have three options. One is the direct specification, which means that the mass proportional coefficient A sub O and the stiffness proportional coefficient A1, you can directly define their values here. Obviously A sub O was a have a unit of 1 over second and A1 have a unit of seconds. So you can directly define numbers here, so that based on that your C matrix will be constructed by software. The other option is specify damping by period. What you can do here is that you can select two different time periods, just like here in here you have selected two different modes, omega I and omega j. Here you also define the periods, the corresponding periods of two different modes or two different time period values, and the specified value of damping which you want to give to these periods. And then you can calculate recalculate coefficients, and these A0 and A1 will be calculated based on your values given for these periods. So it's like solving this expression, this one at the bottom, solving this expression back for given omega I and omega j and a given xi I and xi j to calculate A0 and A1. So now you can use this option, specify damping by period. The third option is specify damping by frequency, and that is that you can give two different frequencies and their corresponding damping ratios which you want to give to your structure, and then you can recalculate the coefficient. The software will calculate A0 and A1 for you, which will give damping ratios of these values to these two different frequencies. In modal damping, you have to define the modal load case first. Obviously you have to define from where the modal properties should come from. So they should come from the modal load case, and you have to specify the maximum considered modal frequency. If you go to modify show modal damping parameters, you will see that you again have three options. One is the consistent damping for all modes, which constant damping for all modes, which means that whatever value you give here will be given equally to all modes. I mean, all modes will have the same damping ratio, which will be by default number is 2.4%, but you can make it maybe 0.05% damping. The second value is interpolated damping by period or frequency. So what you can do is that you can give the periods, a range of periods, and the damping values. So the software will calculate the modal time periods for your structure and will interpolate values from this table to give to the damping values to different modes. The third option is in second option you again have two options, interpolated by period or by frequency. In case of frequency, you will give these two values. The third option is mass and stiffness proportional damping by coefficients. Is like similar to the same Rayleigh damping, that you directly can specify the coefficients here. You can specify modal damping by period. So you have to give then two different time periods and the values of dampings which you want to give to these two periods, and then software will interpolate and then will assign the values of modal damping ratios for all the important modes contributing to the dynamic response. The third option is specify modal damping by frequency. In that case, instead of giving two different periods, you have to give two different frequencies and the corresponding modal damping ratios which you want to give to your structure. And then if you recalculate coefficients, for example, I give a value of 0.05 and maybe also 0.05. So you can see that the software automatically calculates the coefficient, which is mass proportional coefficient and stiffness proportional coefficient, A0 and A1, which are consistent with these two damping values. So that's how you define damping for any dynamic load case, dynamic analysis load case, going to this tab in load case and then damping. So you can always modify the values, you can see what values you have given, what options you have given, so you can modify these values. So that's all about damping. That's how you assign damping values to your model, your load case, which corresponds to the dynamic analysis. So thank you for this lecture, and we'll see you in next lecture. Thank you.